I will clear the statement 5 and the question 8. If you are clear, can you raise your hand? Shahama, clear with question 8. By question 9. Shahama, you okay with question 8? Question number 9, it's answer number 1. Hope it's clear. By question number 10. In question number 10, what can you tell about the potential difference across the resistor in A and B? Are they same or different? In question number 10, the potential difference across the resistor R, is it same or different for A and B? Can you hear me, right? It has to be same. The reason, how are the cells connected? How are the cells connected? The cells are in parallel. The cells are in parallel. Therefore, V equal 5 volts in A and B. Okay, Sarah. Did you observe that? In A and B, in A, all the three cells are in parallel. So, the potential difference across R will be same. Okay. Now, among these graphs, we have only two possible answers, 3 or 4. So, which one do you think is more suitable, 3 or 4? Shahama, are you clear? with this argument? Are you clear with this argument and how we eliminated 3 of the answers and kept 3 and 4? So what else? Is it the third or the fourth? So just think, what will be the advantage of having 3 batteries? Sacha, you have 3 batteries in A and 1 battery in B. Okay, so who has more power? Who can deliver more power for a longer time? A or B? It is obvious, right, that A must be able to deliver more power for a long period of time because we have 3 batteries. But in case of B, we only have a single battery. So the answer has to be 4. Is it clear? 3 of you clear with that? Since A has 3 cells, it can deliver power for a longer period of time. For a longer period compared to B. Okay, Shahama, here we have 3 cells. We have 3 cells connected in parallel and they are identical. So this is 5 volt, this is 5 volt, and this is also 5 volt. So what can I tell about the potential difference between these 2 points? That is the terminal voltage. It will be identical or it will be same, right? Sorry, not the terminal voltage, the EMF. The EMF of these 3 batteries, the EMF of these 3 batteries, or the identical cell of these 3 batteries still will be 5. Let's say it is 5 volt, internal resistance is R, R and R. So the equivalent setup will be 5 volt, 5 volt with R by 3. Okay, Shahama. So the terminal voltage will slightly decrease. The terminal voltage will slightly decrease. Here the resistance is R, here the resistance is R by 3. Okay, they have mentioned the internal resistance is negligible. So just forget about the internal resistance. So forget about the internal resistance. So this is the identical setup. Okay, Shahama. Are you clear with this statement now? So this is okay. Now the second one. Using this statement, we eliminated 1, 2, and 5. So 3 or 4 remains. Here, A has 3 cells. So it has a lot of energy. It has a lot of saved energy, conserved energy. When it is compared to B, where B only has 1 single cell. So A can deliver power for a longer period of time compared to B. Now look at the charts or look at the graphs between 3 and 4. The fourth one is more suitable, right? Got it? Okay. Now 23. Question number 23 is now easy. It should be very much easier. What is the answer of question number 23? What is the answer? You have two cells in parallel with internal resistance R. So the equivalent is R, En, internal resistance is R by 2. Therefore, the fourth one. Okay, it's the fourth answer. Next topic. Maximum power discharge. Maximum power discharge of a circuit. We have a battery with EMF E and internal resistance simple R, which is connected to a circuit of resistance capital R. Now, the current in this circuit is I. The current in this circuit is I. So let's find out. Let's get an equation, or let's get a relationship for I. E is equal I into R plus R. So I is equal E over R plus simple R. Now, let's get an equation for the power dissipated in this resistor. We know that the power dissipated in the resistor, the power dissipated in the resistor, R is given by P is equal I squared R. So instead of I square, we can substitute E square over R plus R square. So P is equal E square over R plus simple R square into R. Okay. So if R is 0, then from the equation P is also 0. If R tends to infinity, if R is getting higher and higher, that means R is very much greater than simple R. Therefore, we can write that P is equal E square over R square. How is this? When you add a very large number with a small number, it doesn't make much difference. That is why I straight away wrote it as R. Since R plus simple R almost equal to capital R. So we can write that P is equal E square over R. Now, if R is going to infinity, then P is going to 0. Now, if you check when we have r is equal to 0, when r is equal to 0, it is 0. When r is going to infinity, also it is going to infinity. So, somewhere in between, we should have a maximum, right? Somewhere in between, we should have a maximum. Then only it's possible, right? Starting from 0 and going to 0 means there should be some turning point where it's maximum. Mathematically, it can be shown, or it can be shown that P tends to P maximum, or P is equal to P maximum when R is equal to simple R. So when external resistance equal to the internal resistance, R is equal to internal resistance. So P max, okay, I'll scroll up. For now, let's try to understand this. So P max is equal E square over simple R plus R square into simple R. So P max is equal E square over 4R. Once you have copied down, let me know. Did you get the idea what is happening here? Once you have copied, let me know. Done. Sahama and Saja. Completed. So here is the idea clear. Here what we have done is we are trying to find what is the maximum power dissipated in a circuit. Okay. Here we got the equation, and from this equation we check when R is equal to 0, what is the power dissipated? We get it to be 0. So that is okay. Next, what we do is we see when R goes to infinity. When R goes to infinity, R is very much greater than simple R, right? So the equation reduced to something like this. And when we plug in R to be infinity, or R tends to infinity, we get that P also tends to 0. So starting from 0, ending at 0, that means somewhere in between it should have a turning point. It should have a turning point. So that turning point will be the maximum value because it cannot go beyond that. So mathematically, it can be found that the turning point happens when the external resistance is equal to the internal resistance. So that is the maximum power dissipated. Okay. So yeah, if you have any questions, in the past paper asking you to find the maximum power dissipated, then what is the thing you have to do? You have to equate the internal resistance, you have to equate the external resistance to the internal resistance. Okay. So next, let's start a new part, Kirchhoff law. Kirchhoff's laws. We have two laws. The first one is KCL. KCL. Kirchhoff's Kirchhoff's current law. Kirchhoff's current law. So here it's like this. When we have a node, the current flowing to the node, let's say it is I1, I2, and I3. I1, I2, and I3. The current flowing out of the node will be I4 and I5. What Kirchhoff says that the algebraic sum of currents, entering a node, entering a node is 0. According to him, I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. Or you can rearrange it as I1 plus I2 plus I3 is equal I4 plus I5. So here, this law is actually based on the energy conservation. The charge conservation. The charge coming to the node has to leave the node, right? Both the charges have to be equal. So that's the simple idea. The law is based on based on charge conservation. We know that current is charge. Here we use positive and negative, right? So it's simple. The current entering the node, current entering the node is considered positive, is considered positive, and that leaving is considered negative, is considered negative, or vice versa. So you can consider anyhow, the opposite one will be negative. So did you understand in simple what is Kirchhoff's current law? Rahama? Okay. I will not. Shall I scroll down? So second law is KVL. KVL. Kirchhoff voltage law. When we have a circuit, let's say this is E1, R1, E2, R2, and this is R3, R3, and there is a current flow I in this loop. There's a current flow I in this loop. So here, what he says is the algebraic sum of EMF, algebraic sum of the EMF in a loop, in a closed loop is equal to the algebraic sum of the potential drop in the loop. So here if we check the EMF, so now we are going to consider or this law or this or the total the total 1 minute right up to this of sum of voltage rise equal sum of voltage drop. Simply, we can tell the sum of voltage rise is equal to sum of voltage drop. So where does voltage rise occur? In batteries. That is what we say sigma of EMF. And where does potential drop occur? Across resistors? That is the sum of potential drop. Okay. So here, if we check the EMF, if we check the batteries, these two batteries meet in the opposite direction. So sigma of EI, that is E1 minus E2, equal I R1 plus R2 plus R3. Okay, note of this. The final one, is it clear? Yeah, how about you? Okay, so let's try a few examples. What is the current I? So here, can you remember the convention? The current towards the node or the current entering the node is positive, current leaving the node is negative. Okay, so according to that, apply and find. Very clear. 4 ampere enters the node. Because the value came in negative, that means the direction I have considered is incorrect. It should be in the opposite direction. So here I have considered it as leaving the node, but actually it is entering the node. Okay, is everyone clear? Shama. Okay. We have to find the current I1 to I4. Start from some corner and try to find it. So it is just like a puzzle. You can start from somewhere. Try to check. Start from I1, I2, I3, and I4. See which one you can find first. So the idea is simple, right? The current entering the node is equal to the current leaving the node. Here, which one is easy to find first? I1, I2, I3, I4. I2 is easy. What is the value of I2? Here, this I2 current has to divide as 3 and 7. Therefore, what should be I2? See if you have got this answer.